Okay, so this is probably my second or third time talking at Tower. It's my favorite online conference. And thank you for having me talk about something that I'm passionate about, which is introducing Python into core university mathematics. So I will give you a rundown of what I'll be talking about. Okay. Right, I'll be defining what I mean by core maths curriculum. I'll show you examples from various topics that I'm sure all of us um, have at one point or another taught. I'll give you a couple of case studies that I teach, the modules that I teach at Warwick, and how I embed Python into those modules. Here is one first year module um, on vector calculus, and another third year module, quite a different one called problem solving. And I'll end with some practical advice about how to get started and whether we need to be fearful about AI doing all the coding and all that kind of thing. Okay, so here's what I mean by core maths curriculum, and I'll be focusing on the first and second year materials. We've got the usual pure stuff, real complex analysis, maybe linear and abstract algebra, calculus, maybe a bit of differential geometry, differential equations, dynamical systems, probability and statistics, of course, and probably at your university, you have a module on coding, be it Python or maybe in MATLAB or whatever language you've chosen. And that's usually a standalone module. And my point today is that there is definitely a point to having that module, but it doesn't mean that computing has to be confined to that module. And I think computing should be a part of all of these courses that I've listed here. Okay. And there's a little asterisk there about dynamical systems, because this is a topic that Stephen will be talking in his talk next. Okay, so I won't be covering that topic. So why Python? If you're here, I probably don't need to motivate you too much about why we should go with Python or have Python in our curriculum. Apart from the fact that it's still probably the most popular programming language in the world at the moment, things might change. But at the moment, apart from that aspect and the employability aspect, what about math? Why should we care about Python in maths? It helps you do calculations, of course. We can use it like a calculator and speeding up tedious tasks. You can do simulations on it easily, probabilistic situations, game theory kind of situations, statistical kind of thing. It can happen in front of your eyes and you can see results. Okay, visualization is a big aspect. Apart from plotting graphs, you can do 3D stuff, you can interact with it, rotate things around, sliders. You can have animations, and I'll try to show you some of these features today. Here's probably the most important aspects from a pedagogical point of view. It allows extension, as in, here's a problem, do some coding on it. What else can you say about a problem? So using the numerical evidence that you gather from Python, and what can you say? Make some conjectures and maybe prove them. Okay, so that's a really important part of why we have Python. Okay, here are some examples, and from time to time I'll come out of the presentation and show you some code. Um, Probably all of us remember that first time that we saw this definition of continuity of a function at a point, and we're scratching our heads. Oh, what does this line mean? And your students are doing the same. Continuity at a point x naught if for epsilon greater than 0, the x is delta positive such that this happened. It's something that Python can help you out with. And let me come out of my presentation and show you a little code. So I'm going to show you a function And this function is log of x plus 1. And I want to study the epsilon delta continuity at x equals to 1. Okay, so I'm going to be producing this plot at x equals to 1 here. And the name of the game is to give me a delta if I give you an epsilon. Okay, so I'm going to provide the epsilon via this little slider. And the code is going to tell me what delta should be. Okay, so what can you do? If you try to draw this on the board or show a slide with this static picture, it's really not doing this justice, really, isn't it? Because it's about changing, the dynamic of changing epsilon. So here's a little piece of code that doesn't require too much high-tech coding at all. I'm using IPy widgets here to make the slider, but you don't have to. You can just use matplotlib. It's equally valid. And here's the result. And the slider here allows you to control delta, which is this, allows you to control epsilon, which is this neighborhood of F1. Okay, so this is going to change how big that neighborhood is. And the point is, where is that from? How is this map? It came from mapping some delta neighborhood of 1 here. How big is that delta neighborhood? You can see from the picture that this function has kind of lopsided neighborhood here. So if you were to take a biggest delta, it would have to be this left number here, isn't it? Yeah. So I think that you can talk for ages around this this little app, really, and you don't need fancy coding skills to make this happen. I think this is my point. Yeah. Okay, right. So let's go back to my thingy. So that's an example from analysis, and a nice thing is that not only you can find the delta, you could calculate it and see if that corresponds to what Python is telling you. And this is the calculation for that delta. And I find this 0.2438, exactly what Python is telling me. So that's kind of harmony between theory and practice. Okay, that's nice. Okay, next I have an example from group theory. And there will be people in the audience who are algebraists, and I apologize for my poor explanations of things to come because I'm a theoretical physicist. Okay. So I'm going to be talking about the symmetric group S4. If it's been a while since you've done this, S4 is just a group containing this kind of permutations. Okay. And we use this kind of permutation brackets to say 2 goes to 3, 3 goes to 2, 1 goes to 2, 2 goes to 3, 3 goes to 1, that kind of cyclic notation. And you can decompose these things into products of 2 cycles or transpositions. If they can be decomposed into even numbers of these, you call it an even permutation. If 1 or 3, you'd be odd permutation. So yeah, it's a number of transpositions that it can be decomposed to. So here's a group of permutation of 4 symbols. How many ways are there to permute 4 symbols? 4 factorial. So that's 24 of these guys. I've given them labels from 0 to 23. It's pretty much arbitrary how you label them. Just wanted to identify them, that's all. And I've shown you whether it's odd or even. Okay, and it forms a group. And you might be curious to produce a group multiplication table with this. Of course, you're not going to do this by hand in class. Probably when we teach these things, we go with smaller things like S3, and nobody wants to write a 24 by 24 table on the board, right? Okay, but Python can, and with a little code, you can produce this kind of table. And you might be thinking, okay, well, obviously you're an amateur because nobody in group theory uses Python. We're good with Magma, we're good with Sage and Gap or whatever you have. But yes, those are probably better tools to do algebra with. But you should probably think about, are they going to be using Gap and Magma and Sage after they graduate, or are they more likely to be using Python? And I think we all agree that Python has a more kind of long-term payoff. This is something you learn once, maybe in a computing module, and you can apply to all these modules without learning extra syntax, extra, things. I think it's okay to just at this kind of introductory group theory level, it's perfectly fine to use um, to use Python. And I'm not using any special niche kind of libraries at all. It's just basically SciPy, NumPy, Matplotlib, and SymPy for some of these things, but that's it. Okay. And once you've got this very colorful table, you can now take mathematical information from it, and you can probably spend a good 10 minutes just talking about how this table looks like. For example, you can see subgroups in here. For example, this top left block here, it's 0 to 5, so 6 symbols. What is that? That's S3, permutation group of 3 symbols. What about these guys? It's 0, 1, 1, 0, that's S2, 2 symbols. Okay, so S2 in S3 in S4. And you can see, oh, what's happening here? There's blocks. What are these blocks doing? And these blocks are like self-contained blocks. 6 to 11 are staying in their own little world. 12 to 17 are staying in their own little what's going on here? You can spend another 10 minutes talking about cosets. You're basically, things are organizing themselves into partitions, and these are partitioning by cosets. Okay. And yep, so lots of information there. And if I rearrange things into odd and even, so I've put all the even permutations on top and put the odd ones at the bottom. Yeah, so rearrange them. I see this structure. And it's very intriguing because when you step back far enough, you see 4 blocks. And what are these 4 blocks? Well, these you recall these even permutations themselves form a group, a little subgroup of S4 called A4, the alternating group. And this tells you that standing far enough from this colorful table, you see is sort of like, even, odd, even kind of structure. So it's like a multiplication table between 0 and 1. That is an isomorphism that's coming out from this quotient group. Okay. So I think that's a kind of visualization that I want people to be aware of, that Python can do this for you. Okay. Right. Next thing I'm coming out of the presentation again, this is linear algebra. And when it comes to teaching eigenvectors, yes, you can do some sketching on the board, but it's more fun to interact with it. Okay. And this is a little thing that I came across when I was a student. It was using MATLAB. There is a MATLAB page, almost like a MATLAB guide page on how to make this game. And I thought, oh, I can make this in Python now. And let me show you how that looks like. Okay, so this is show was the name of that MATLAB function. Some of you might recognize this. And if I run it, let's see what happens. Okay. And it's going to be a game where we're going to input a matrix. In this case, I put in 1, 1, 1.5 and a half, and I'm going to multiply that to vector x, and vector x is going to be this endpoint in blue. I'm going to use theta to make the x go around. So basically, you're interested in the direction, not really interested in the magnitude. So changing x and multiplied by matrix A, AX becomes this red thingy here, okay? And the goal of the game is to make the vectors parallel. They're parallel here, and they're parallel here, and they're parallel here. And here basically are two directions in which they're parallel. What are they? They are the eigenvectors, of course. Yeah. And I've plotted in green. I've used um, I've used Python to tell me about the eigenvectors of the matrix. So you can change the matrix and continue playing this game. For example, I changed the matrix to, if I change this to, let's say 0 0.5, 0 0.5, let's see what happens to that game. What's this one? And you can see that it's the same game as before, but at this point, is that parallel or not? Not really sure because it's gone to zero. This is because there's a zero eigenvalue involved. Yeah, the eigenvalue is telling you about the magnitude and the relative difference between the magnitude of the two arrows. Okay, again, don't let me start on this thing because with one of these visualization things, you can keep on talking about it, isn't it? Yeah. And I think maybe the point is to make your student do the talking and given a visualization, talk about it. What can you learn from it? Okay, I've got a couple of things to show you quickly. Won't talk too much about it. Here's one on PEs. So we've got, if you're teaching PDEs, here's wave equation with initial conditions and initial velocity and some boundary condition. Okay, and boundary condition is happening on a square. It would be really difficult to try to, I don't know, to draw this in class because it's pretty much impossible to draw. But it's so much more exciting when you ask Python to do this. And the code is not too horrible. If I run the code and you see the animation happening with time, and it's quite mesmerizing. It tells you that as time progresses, you can see standing waves happening thanks to the nice initial condition I've set it so that you see this fundamental modes here. Okay, so animations, you can save the animations as MP3, sorry, MP4, and these are things that people can just, maybe you don't care about the code, ask your students to just submit the videos maybe. And also another thing that is fun to look at is the maybe something from complex analysis. Zeta function. I mean, there are lots of videos on YouTube that shows the right-hand side here of this thing doing kind of loop the loop, lots of really funky things happening. But I think it's much more educational to look at this as an actual mapping. This is a complex map which takes some complex numbers to another to another set of complex numbers. Okay, and what we're interested in is the image of the fundamental line, well, the top half of it. We're going from 0 plus half I, and we're gonna go along this line. Okay, half, sorry, not 0. Half plus something I, and we're going to go positive numbers. The imaginary part is positive. So we're going to change this thing and just go up because, it's kind of, if something's a root up here, the conjugate is also another. Okay. I told you to stop me from talking. Okay. Because you can go on for a while. But let's see what happens when I look at the image of this thing traveling up, apply the zeta function to it, what happens, and you see a lovely little animation. Hopefully that will come up. Okay. Oops. Look at that. So the left hand side is traveling up, and the image is that side. This is the origin. Hopefully it's coming back to this point. That's the first root of the zeta function found. It's still traveling up, and it's coming back to the second root now. And three. Okay, is still going up. So basically, it's going to be going through the origin 10 times in this animation. That's the first 10 non-trivial zero of the Riemann zeta function. And once you have this code, you can basically put in any kind of complex map you like, and you can teach things about conformal mapping, Möbius maps, and all these kind of things with basically Python. Okay, so that's nice. Okay, next three things, I'm not going to show you the code, but let's play a game where you guess what I'm talking about. Okay, so stare at it for a few minutes, and if you were to teach probability and the code produces this, what do you think you are teaching? Okay, winning probability, winning stay. Okay, yes, you're right. This is the Monty Hall problem, and it's a simulation of the Monty Hall problem. And of course, you can add to the code, add more doors, more ghosts, more cards, what do you like? Okay, right. Next one, guess what this is? Probability is greater than half when group size exceeds 23. You'd be right if you said this was the birthday problem in a group of more than 23 people. The probability that two people have the same birthday exceeds 0.5. And you can do a simulation on this. Yeah, make number of people increase and give them random birthdays and see how many matches and that kind of thing. Okay, so things that aren't intuitive, you can see is happening right in front of your eyes. Okay, last one, what is this? This is a little bit slightly more niche. Probability that a needle thrown randomly intersects a grid line. This is the Buffon's needle problem, and you can adjust the size of the needle and the line, and you can get an estimate of 1/pi. I read stories about how teachers try to do this in class, and there is no hope you can do this in class because you need to scatter I don't know, like 100,000 needles before it becomes 1/pi. The convergence is just so bad. So don't do this in class ever. Okay, but do this on Python. Okay. Okay, that's my first bit showing you the power of Python in various applications. Okay, quick run through case studies. This is my first year vector calculus. Is core module for everybody. We have a large class, about 350 students. And the syllabus is pretty much vector calculus kind of thing. Vector descriptions of curve, partial differentiation, grad diff curves, surfaces, multiple integrals, line integrals, and we end with Green's theorem, Stokes' theorem, and divergence theorem. The module has 4 assignments with one Python task in every assignment. So it's, let's say if it's a 20-mark assignment, I would put in maybe 4 marks for Python, just to make everybody do it. And for example, and if you have been to my previous Talmud talk, this would be recycling of those materials, so apologies. And this is one of these problems. Here's a circle rolling in another circle. The blue circle is rolling in the bigger circle, and you want to trace out the path of this red point P. Giving you the equation, use Python to plot the curves corresponding to various R, which is the ratio of the small radius to the bigger radius. Okay, and see and plot them and make one conjecture on the appearance of the curve for arbitrary R. So this is I think B is really valuable in terms of the pedagogical value. Look at the Python output. What can you say mathematically about it? Okay, this is first year, so I didn't make them prove anything, but just coming up with a conjecture is a great practice. So here's some Here's the code demo. Let's do a code demo of that. So this is my own code. I'll put the radius to be 1/4, and if this black circle is going to be rolling. Okay, the black circle is going to be rolling, and you can see this spirograph thing if you're feeling nostalgic about those kind of things, and it's forming this little asteroid-looking thing. Let's try to put in more weird things like 1/pi. What happens instead? You see things that don't quite close up, and it just keeps on not closing up. Okay, so that's, and what can you what kind of conjecture can you make? You can experiment with all kinds of values here. So let me show what our students wrote. Um, here is a submission from a student, a little code snippet with all the things that I asked for. The curve will not form a closed loop when the value is irrational, and will do so when R is rational. Perfectly fine. Okay, and maybe you need to be careful about this thing, whether is this closed or not. It's a straight line if the radius is exactly half. Here's another output from a student's submission conjecture. If R is rational, then the point P touches the outer circle in Q unique points. That's a nice way to put it. If not, if it's irrational, it touches the outer circle infinitely many unique points, which is interesting conjecture. Very good. Okay, here's another one. Another assignment has this thing where it says plot the torus. Here's the vector equation of a torus, sorry, parametric equation of a torus, and plot it and include some screenshots. Do I care about your code? Not really. If you show me the code, that's fine. And it's about maybe making a pretty output. Okay. And I've given them a bare bone code here. Here's like a minimal code for plotting a surface, and embellish this and make it your own. And here are the submissions. We've got very good submissions from our students. Very colorful donuts. Okay, here's the third year module. That's a little bit different, called problem solving. So this was inherited from the educational department when it was, well, before I joined Warwick. And it was based on very good book on kind of pedagogical aspects of problem solving. Mason, Burton, and Stacy Thinking Mathematically, really highly recommended, where they talk about breaking every problem down into three phases: entry, attack, and review. And then these keywords that people should try to use when writing up the solution. So assignments, it's not just about writing a mathematical solution, but writing a rubric incorporating all these keywords in the margin. Okay, this is my entry phase, and here I know I introduce whatever, and when you're stuck, you write you're stuck. So it's more about the problem solving journey and how you get through the problem, and you enter a review phase where you reflect on what you've used and how you might extend it. And this extend phase is great for Python, and you can make the problem more difficult. And if you don't know the answer, maybe get Python to shine some light on it and then make conjectures on it. Okay, fine. So here's one example: lines and squares. So the kind of problems we've solved are kind of Olympiad-y kind of thing. Consider the pictures below. In the first picture, there are 10 straight lines and 17 squares. Let's look at this. So if we just count the 1 by 1 squares, obviously that aren't enough. There's just 12 of these, where the 17, well, it's also the 2 by 2 squares are also counted, right? Second picture is 9 straight lines and 20 squares. So it's talking about squares of different sizes. Find the smallest number of lines needed to make exactly 100 squares. So yes, there is just things that you can do without Python. You don't need Python to do this and come up with the answer. I won't tell you the answer if you want to think about it a little bit. But what can Python do? Once you've solved that initial problem, you can use Python to generalize generalize. So the question, okay, what if I want the smallest number of lines needed to make exactly n squared? What's the formula like? And it turns out it's not a straightforward formula, but you can make some approximations if n is large enough. And this is, for example, one way to do this. The number of lines as a function of given number of squares required. If n is large, then you see this blue line. That's the approximate solutions. But exact solutions are all these red dots. So there are lots of different answers. Okay, and you can talk about the origins of these little lines here as well. And if you want 100 squares, the answer is somewhere around here. These are not overlapping things, okay? There's only one dot with the value of 100 here. They're just a bit close together. Okay, so that's the kind of thing I'm thinking about using Python for extending, making conjecture. Okay, and maybe when you just write a code to do this, you don't expect this blue line. When I did it anyway, I didn't think about this approximation. But when I plotted it, I go, okay, there's a lot of things to unpack here. And the lower bound was very apparent. And then you look at the equation again, okay, actually, yes, I see where the lower bound is coming from. You can talk about the upper bound too. Okay, so it's a lovely way to do what I call Python-led extension, Python-led conjectures. Here's another one. Is a more famous problem, I think. In the big bowl, number of strings all jumbled up, and you put a blindfold on and reach into the bowl of strings. You randomly choose two ends, tie them together, repeat this process, and once you remove your blindfold, you find some closed loops have been formed. Investigate. So there isn't really a question there. It's up to you whatever you want to investigate. It's up to the students to go, okay, I'm going to think about maybe the number of loops or the length of loops, so whatever you like, basically, however you interpret this. By the way, I asked Bing Copilot to come up with a suitable graphic for this, and it's not done a bad job, is it? It's quite good. It's a bit I mean, there's no need to put your head into the bowl, but it's perfectly fine. But it also gave me a different option, which is okay. um right. So let's see what our students made of this problem. So these are some of the things that they did, apart from all going through the maths, starting from simple cases, going through, this is the extension phase, where this student, for example, uh, limited the number of trials, so 50, 100, 250, and 1,000, and looked at the distribution of number of closed loops. And this is what they got here. This student went further on the right here, did the same thing with with a large number of samples, and tried to fit a log normal distribution on top of this. So that's great. Yeah, let's try to spot the distribution. It's probably not something you could have done by hand, I don't think. And this is yet another student who not only thought about the number of loops, but how long are the loops of these strings that are formed. And it's got this little distribution. And of course, they tried to explain why there's a peak here and what shape is this, why is there a dip here, that kind of thing. So these are students' ideas of Python-led extensions. Okay, so I've given you a lot of ideas about how to involve Python in your teaching. Here's some practical advice, because not all of us here are expert Python user. I'm not sure I consider myself an expert Python user. The code I normally write are simple. I don't use professional kind of idioms, but yeah, I think it's been very, very, very good for my teaching. Python enriches maths courses. It deepens students' understanding and encourages mathematical curiosity. Hope I've convinced you of that. If you don't know where to start, why not start by including a small Python task in your homework that you already have. It doesn't matter if you're teaching analysis or group theory or whatever. There's probably an aspect of thing where people could use Python to to do some calculation, some simulation, some visualization. I'm sure there's an idea somewhere. If you're not confident with Python at all, why not get students to co-create some tasks this summer? Maybe you can offer it as summer internship. If you offer it to maybe a more senior student and ask them for ideas about, okay, how do you think there's a Python idea somewhere? Coding really isn't the main point. In fact, for the assignments that I asked for the third year module, I say, okay, put it on your GitHub page. Tell me the GitHub link. That's it. Okay, and I just look through whether the code exists or not. Maybe you want to run random codes from time to time. It's fine. The code isn't the main point because probably your students are asking ChatGPT to do something, maybe. And ChatGPT 4.0 was in the news 2 days ago. I checked yesterday. I thought I would be able to show you something about it, but no, it's not rolled out for me yet. So sorry about that. But I did try to ask ChatGPT 3.5 to do some of the tasks that I showed you to plot maybe the epsilon delta slider thing. My prompt engineering skill isn't advanced enough to make it do exactly what I wanted it to do. It involved too much of me embellishing it afterwards. It's so much easier to do it myself. But anyway, I think we have to accept that AI assisted coding or purely AI coding is going to be the norm, and this is what you have to accept. And many students use AI to create some rough code and then embellish. And this is told to me by students. So I'm pretty sure this is what's happening. And probably your students too are telling you that they're kind of openly telling you this. So why not give students some basic code and ask them to modify? Coding isn't the main concern for us mathematicians. Anyway, if you want some mathematical payoff, it's not about the code, it's about what else? What does the code tell you? Beautiful coding isn't important unless your module is computing. Then, okay, you want to say, okay, you've got a lot of redundancies in your code. You've done this wrong. This is very inefficient. You've got machine epsilon problems going on. Those are all important topics to cover in maybe like a first year computing course. But after that, it's more important to interpret your code output, to use the code to verify theoretical results. It's not just about coding. It's about making bold conjectures and to dig deeper into the math. What else can you get from this problem? And this is this phrase that we throw around so much, critical thinking. I think this skill exactly exemplifies what critical thinking is. Yeah. Okay, so here's my conclusion. Python can help students gain solid understanding and develop mathematical curiosity. I hope I've convinced you that that's the case. You don't know where to start. Start small, maybe one homework problem. And if you are comfortable with going big, why not have a whole module that's assisted by Python? And again, I don't think we maths folks want to introduce a module on coding, but module on what coding can tell you about maths. This is my point. Yeah. Students can help to co-create and test content. It benefits everybody. Your students aren't afraid of Python, and neither should you be. Okay, lots of great resources out there. And if you like what you saw today, the code that I talked about are in my book. Sorry about this shameless plug. And it's a book that I spent a couple of years writing. So exactly on this topic, where how to include Python in our day-to-day teaching. If you don't have access to this book through your library subscription, and you want to know about certain topics what's in the book on certain topics and chapters, feel free to write to me. I'm happy to discuss and show you some things. Okay, right. That's the end of my talk. Thank you. Thank you. Look at it.
Right. Thank you very much. Thank you. I'm sure people can give a round of applause. There are reaction icon emojis as well for that. We didn't arrange who would be dealing with the questions, so I've put in the chat if anybody would like to send some questions. There aren't any questions in the Q&A yet, so if somebody wants to put a question there, that'll be fine. In the meantime, I do have a question. You say that the students aren't afraid of Python, but I've found some of them are a bit reluctant to use it. Many of our students don't do computing because they don't like programming aspects. And so, I mean, what do we do with these students who are a bit reluctant?
Yeah, are these I guess these tend to be um students who maybe didn't do computing in school and this is the first time they've done programming at university, right? It's true, yes, I do have these students too. I think it's about showing them that coding to be um, doesn't have to be always from scratch. If you don't know where to start, it's perfectly fine to use somebody else's code, embellish on it, change something about it. And I think that's a good way to go about coding. I think the most difficult step is to, okay, here's a blank document, fill it with code. That's the most scary step, isn't it? But if you already have something that runs and you just need to change something about it, I think that's a great way to kind of make you think, actually, I can do programming. Actually, I'm not always facing error messages. It's so scary when you learn programming and you just spend your whole day, yeah, sorting out bugs and red warning messages. It's not a nice feeling. But if you start with something that runs, change a little bit here and there, I think that's a way to ease people in.
Right. But what if they've got, now there's a question here from Chongchitnan, but what if they have no Python programming their background? I mean, do you
Mm,
worry about losing students who didn't want stroke expect to deal with the coding in a given module?
mm. I think it's yes. I think we still have a responsibility to put a compulsory computing module. I'm not saying we should get rid of that. So if you don't have programming background at all, there should be something, we shouldn't say, oh, if you join this program, we expect you already know Python. I think that's not right. I think we
Right.
should have a first year compulsory module that deals with the coding aspect. But in all the other modules, we shouldn't be afraid to ask them to do Python things too. That's my fault.
Yeah.
Mhm.
Okay, we've got another question from Ian Charlesworth. Is the code available for the interactive examples you were showing at the start somewhere? The eigenvectors one was quite nice, apparently. So
Yeah, they're all in my book, and the book has a GitHub page. Basically, uh, if you I don't know, search for me on GitHub, Siri Warwick, you see,
right.
and the code are
We'll see
all
if we can get.
available for free.
Yeah,
Yeah,
I'll see if we can get that
yeah,
into the chat because somebody's also asking about that, the
yeah,
name of the book and the link.
cool.
And there's a comment from one of my colleagues here, Richard Elwes. Just a comment for a big module. One obstacle is recruiting enough Python literate markers stroke tutors. I mean, do you have a problem with that? Have you got
Mm,
solutions?
yeah. So I don't organize the computing module that has to do with this. My colleague does, but he's um kind of expressed the same kind of sentiment where it's not always easy to recruit markers for code, and it's not fun to mark codes. I've done it myself. Marking code is probably one of the most soul destroying things, especially when you have to do hundreds of these. But yeah, I know what you mean, and especially maybe if you're trying to recruit from the generation of students who didn't have Python in their diet, and now making the market, I think that's more difficult. So I don't know what the answer is, but I can sympathize that it's happening. Yeah, I think it will be less of a problem as the years go on because people will become more and more, okay with Python and having had more exposure. Yeah.
Okay, thanks.
Yeah.
I'm aware that David has his hand up, but I mean, unfortunately we're running out of time here. So, David, if you want to put the question in the chat or in the Q&A, that'd be great because I would like us to have a break from the screen before we come to Stephen. Can we thank Siri once more? There's emojis and under reactions. You will find
Yeah.
some things. I don't know. I can't even find them now. There we go. There's a clapping hand there. And then I think we should stop there for, should we say 5 past? That should give us enough time to get a cup of tea at least or a cup of coffee. Yeah. And then we'll have Stephen at 5 past. Yeah.
Yeah.
Okay.
Okay.
Right. Well, thank you very much. We'll see you in a few minutes.